Right here, you can see the sensor there, and the sensor there, and the sensor there. And the coding tool has to hold a vacuum, and that is achieved using this ribbon cable here. And it has to be flat, so the coding tool can close. The current tool works, but it breaks very easily. It's very delicate and fragile, and it's really expensive to replace. It's around $25,000, so I'm trying to cut that down. The problem statement to our project is to design or improve a tool that measures the spacing between the two parallel plates I've been talking about, and that's accurate up to that 1 thou spec, or 0.001 inches. Again, the tool must be able to hold a vacuum and seal properly. The calibration head must be able to withstand up to 75 degrees Celsius. The sensors must be accurate up to that 1 thou spec. The calibration head diameter cannot exceed 9 inches and cannot exceed a height of 0.08 inches. It has a budget, and we had a budget to work with about $2,500. And these distances, like the 9 inches, they aren't that much. They can be, we can make smaller plates or various sizes, so that's what we chose to do. We chose to make some adjustments to the current tool, designing our own stuff. We manufactured and designed the calibration head using some software. This means we were making our own new custom plates with O-rings to hold the plates at certain positions because they need to be able to vary. We also designed our own custom capacitive sensors, and we also needed to use a section of flat cable to keep that vacuum seal in the codec group. We also made a new control box you'll be able to see over at the table, as well as coding and designing a way to read the new sensors we just made. This year timeline is an approximation of when this the calibration head is needing to be recalibrated. We need to actually recalibrate our own design. So this needs to happen every 6 months, as shown here on the timeline. Here is the system diagram of what we're working with. In the big gray boxes on the very outside, you can see it says inside of the coding tool, where our calibration head will be placed. Then you see the user interface on the right side. So we have our 3 sensors inside of our calibration head that are going to be connected through coaxial cables that run through that ribbon cable, that flat piece that I talked about, into our microcontroller, which we used in STM32. For the plate design, I used a stack design when I was designing it. This was, as shown here, you can see I can run my wiring from the sensors, from the sensor plate, right through that, and I don't have to worry about anything extruding outside of the plates. We decided to keep the same plate diameters that GlobalFoundries is currently using, and we decided to thicken the bottommost plate to make up for some measuring distance between where the sensors would be sitting. That way we'd have a little more accuracy. For our sensor plate, like I just described, they're going to have 3 sensors. Each of those are going to sit right there. These little holes right here are going to be for our variable measuring device that is designed, and the wiring plate where these sensor wires can run out through in one area. Here's a little section view of what it looks like when it's all put together. You can see those pins that run up and down that can change heights, and you can see the where the wiring will come right there from the sensors. So the variable measuring device that I decided to go with was using a pin and receiver type style. That way the receiver could hold a rubber O-ring in it. This is where it would sit. And that's to be able to hold this top plate, as shown here, at a certain distance above that bottom plate, so we can get accurate measurements from our sensors. It turns out that I couldn't meet the 1 thou. Rather, I actually met, with a lot of testing, I reached 3 to 5 thou instead. So I'm going to need to find a way to knock that down. It is difficult because there's a little bounce back in the O-ring design. And we did try a regular friction fit design where there was nothing but just plastic on plastic, and it's very hard to move 3 of those pins at the same time. So these capacitive sensors work by detecting changes in the electrical charge. So when something comes close to the sensor, it's going to change that reading and detection value. We chose the capacitive sensors because they can detect very small changes when something does get close to them. So they're very accurate. And they're non-contact, so we don't want the plates to be touching. They're going to be hovering away from each other. And we decided to go with a custom sensor design. We tried a circular design and then a star-like pattern. Here's a circular design and here's a star-like pattern, and we ended up going with the circular pattern on the PCB. What you see here are these were just soldered on connections, but these are coaxial cable connections on our final design. So we couldn't find any sensors. We reached out to a bunch of companies and we ended up getting some really high quotes for these that are like 2 inches in diameter for thousands of dollars. So we figured we'd try and come up with our own and see if it worked. And that's what we ended up going with, was a circular design on this PCB board.
So our first idea to measure the output of the sensors was to use an equation. This is going to be hard because we didn't have much time, so we decided to use the STM32 microcontroller's touch sensing capabilities to measure the output of the 3 sensors. So the setup, how it works, STM32, the microcontroller has 8 channels. Each one of those supports 3 sensors each, so there's 4 pins in every group. 3 of the 4 pins can be used for sensing. The other one is a sense capacitor. That sense capacitor stores the charge from the sensor. So what happens is the controller sends pulses to the capacitive sensor, and then when an object is detected, that charge is sent to the sense capacitor, and that's what's read by the controller and returned to us. So this is an example. This is what it returns. It's a raw value. It represents how many charge and discharge cycles it took to fill the internal sense capacitor. So this is the value we started with and worked with. So what we did with that is we created a test setup to test the sensor using 4 different size blocks. They were used to test the sensor's repeatability. So you see on the bottom we have the sensor set in a plate with the spacers and the metal plate on top. And what we did is, using that data, we compared the distance to the number of cycles it took, and graphing these points gave us the curve fit equation that we can input in our code, which will give us any point on that line. So here's the conversion code. It comes partly from the STM library, so when you set up the touch sensing, it returns that cycles value I talked about before immediately. What we added was a conversion to relate the number of cycles to a distance. So this distance value here, that was our equation we found in Excel. And then we also added averaging to produce a cleaner output. So it'll take a set number of pulses and average them together and return one value. A little more on the data. Cycles is the number of charging, discharging cycles. X is the delta value, so that's going to be from when there's nothing interacting with the sensors to when something is brought in. That's the change in cycles. Number of loops is that number of loops you want to take the average, and average is the distance in millimeters between the plates. So that's our final value we want to get. So stabilizing the system, capacitive sensors are very sensitive. They can pick up electrical noise from anywhere in the circuit. Without shielding, false readings and unstable values may occur. So what we did is added coax cable everywhere. It acts as an electromagnetic shield, and that outer braid blocks any interference with the system. So here are some other ways we stabilized. We used PCBs for every connection. So on the left here, these are our capacitive sensors. In the middle, This is our ribbon cable connector, so coax from both ends, and then the ribbon cable connects here. And this is an example of the whole sensor part of our circuit, and this left side would go to the STM. And here's our final schematic of all the major parts. On the left side we have the sensors, which run to the ribbon cable PCB, the ribbon cable, and those tie into the microcontroller. We have our sense capacitor, and 2 buttons for the UI, and the keypad also for the UI.
Sure, and so after we get that data from the sensors, we needed somewhere to store that. So we decided to go with a chip called the serial EEPROM, and that stands for Electrically Erasable Programmable Read-Only Memory. So its job is to retain data when power is removed from the chip or the device that we're using, so our entire project. We're going to be converting calibration data into bytes, which is going to be stored in a set address in the chip, so we can read back from it. And it can be programmed without having to remove the chip off of our project. It has 1 million write cycles, which means you can write 1 million times to it, and it has 200 plus years storage time. So probably long. We're not going to need it for that long. And here's some integration stuff. In the code that I did, I have that WRT variable. That is the values being written to the EEPROM. And then I have some TS variables that are the EEPROM memory addresses. And lastly, the RX buff variable that I used was to store the data read from the EEPROM.
So after getting one sensor to work, the way we wanted measuring distance, the next step was to integrate 3 sensors. First method was to use all 3 sensors in one group. This did not work because one sensor's output would affect the others, so if you put your hand near sensor number 1, sensor number 3's value would change. So since there's 8 groups in the STM's touch sensing, we decided to put each sensor in its own group, and this ended up working and the sensors had no influence on each other. Next was automated calibration. So the first time we used Excel and graphed all that, but Global's not going to be able to do that because they won't get into the software. So we wanted to make a way to automate it. There's an OLED screen on the UI that allows the user to input cycle values for each sensor. So it'll take you through a step process of different distances, and you input the cycle values for each one, and that will, on the right here, this function calculates that power curve we used Excel to calculate before. Yeah. So here's the OLED attached to the UI. So it's going to prompt you with a message when you first turn it on. You can hit button 1 to calibrate or button 2 to measure. In calibration, this is that code I just showed before. It'll start with the 8mm spacing, and you'll input the 3 sensor values there, and then ask you to confirm, and then go to 6, and then on from 4 and 2, and at the end it'll display your power curves. And then it'll go back to the start menu, and in measure mode it'll show you the output of the 3 sensors here.
And for the user interface design, we decided to make our own little custom box. It consists of an OLED and 2 buttons and a keypad that are visible. And the entire system is controlled by the one PCB board that we decided to place inside of it. And you can use the keypad we're planning to use the buttons to be able to select the calibration mode and between the calibration mode and the measuring mode. And we're going to be able to use the keypad to put the user's own input values into it. And I have a couple labels here on the circuit board design that we did. We have some coax connectors where we're going to be connecting the sensors to, the 2 buttons I just talked about, as well as the OLED screen, and into the keypad where we can put our values in from the sensors. And here we have that the EEPROM chip that I discussed is going to store our data. So this is Gantt chart for timelines for our project. Some big key points here are doing this text fixture, which is the entire calibration head, and designing the plates there. I had that done at about week 8 here. And I got into some testing of the adjustable measuring design before that. And a little further down the line, at week 14, I got to research and integrate the EEPROM chip to work with Cameron's code.
So for my Gantt chart, most of the project design is done. The only thing we have left is to finish coding.
That's it. That's a good question.
That was the data sheet, yeah.
Yeah, data sheet.
Can you go back to the O-ring slide? So you mentioned that these are bounce back. That was outside this back.
Yep.
How do you do it?
How does that deal with the bounce back?
Compensate for the calibration.
Yeah, that's what we were working on fixing our equations in the code to account for the fact that we're getting three thou instead of one thou from the bounce back of the O-rings. There's going to be some error.
I'm pretty sure it's consistent
Yeah.
all the time, so you can just subtract or
Yeah.
add or whatever. Can you point to where that thing is in your picture below?
Point to what?
The O-ring assembly.
Oh, okay. Well, it's going to be, it's going to sit in, the O-ring is going to sit inside. This is a little different of a picture, but on our old design, we had the O-ring sitting inside there.
Connect it to the picture down the bottom.
Oh, here. Oh, yeah. So, yeah, these blue pins here are this entire design. There's 3 of them.
What moves?
The plates move up and down. The pin moves up and down, and they're both connected to 2 separate plates.
So the inner cylinder
Yep.
is fixed to the bottom plate.
Yes. Inner cylinder is fixed to the bottom plate, and the upper receiver is fixed to the top plate. Yeah.
Okay. And it's the O-ring's job to hold them in position.
Yeah. The O-ring holds them at the separate positions, so we can take our measurements and send those to the EEPROM chip.
Any other questions?
The capacitive sensors are measuring the distance between these 2 plates, but what are you actually measuring on the tool?
So that tool is measuring the distance between. So it's taking that cycle value and then with our code converting that to a distance value.
Is it the height of the plate? What
All it is, I mean, I can see the capacitive sensor between the top plate and the 2 bottom plates, one's for the wiring. So you're measuring the distance between the second plate and the third plate.
Yeah, it's the distance between those 2 plates.
So but what is setting the distance of that top plate on the actual machine at Global Foundries?
Oh, so that's a fixed height. We had to keep that
Yeah.
0.8 inches the same as their tool. The only thing we're changing is our calibration sequence will be different to where we're going to have the tool step down to those 8, 6, 4, and 2, and then use that data to create the curve fit equations.
So when the machine steps down, it's moving your top plate.
Yes.
Pushing the top plate down.
Pushing the top plate.
Yep.
Yes. And to hold that top plate at those specific distances, that's why we needed this O-ring design.
Gotcha.
You want to show us? Show the crowd?
Sure.
All right, so they're over on the right over there, one of the tables. So let's follow them over and we'll see what they have for us.
we couldn't find a way to not have the springs affect the capacitance values we were getting.
I see.
So, okay. Does this work here?
Yep.
Okay.
So over here, this is going to be our UI control.
Just wait a second.
Oh. Over here, this are really small. This would be read from the machine. So after the machine compresses and you get your cycles, you would put them in here. It's going to prompt you to confirm for each distance. So I'm just putting in numbers now, but and then at the end here, it's going to display the curve fit equations. And we don't quite have the, so here's the equations here. So then these two pieces will be integrated together. We just didn't get the code quite working together yet. But this is in the calibration.
Here. This is where it's going to head into. Your sensors are under here.
Yeah, you can probably pull that right off. Yeah, so this is the inside of the calibration head. These are our 3 sensors with the wire channels coming out here. On this OLED here, you can see the distances. It's not quite calibrated right now, but as you would pull the plate up or down, those values will change.
Will, did you speak about the wire channels?
The wire channels? Yeah, yeah. Yeah, so, and then the chip here I have, this is what it looks like. It's the same as in the presentation that I had. And this is the actual board that we have sitting inside of our control box. This little chip is going to be have that shelf life of 200 plus years apparently, and it's going to be able to hold that calibration data that we that the user has input.
But they can change it, right?
Yeah,
6, 8 months down the line.
yeah, yeah. For every calibration cycle, they can put in their
Did you move the plates? Can you see them live up there?
Yeah, you can kind of see it. It's really small if you guys take a look.
yeah, they're very small numbers here.
If you walk up, you can look at the
Yeah.
actually see the values. So it's averaging, so it's jumping around a little bit, but those are going to be the sensor 1, sensor 2, sensor 3 values.
Any other questions? So these will all be left set up. So between presentations and whatnot, you can come and talk to the students. We're going to have an intermission in a few, after the next presentation or two. So there'll be opportunities for you to ask more questions. But Sam has already set up for his presentation. So we're going to move back. Together. The students here are representing the electromechanical engineering program and the electrical engineering program. Cam is actually in the electrical engineering program and Will is an electromechanical. So we need to make sure that whatever projects they pick and they work on get to mix those kind of technologies together. And that particular project does that. It meets our requirement for that. But it also gives them some opportunity to kind of overlap between them. So Will actually had to write some software, even though he was focused mostly on mechanical stuff at first. And Cam had to do a little bit of mechanical stuff in designing those DC boards to become sensors. And so you see a mix of those technologies, which is an important thing. That's what we're hoping for. As you see the rest of the presentations, again, look for that. Look for that mixed technology, because that's what we're hoping to get out of these. I'm going to turn it over to Sam, and he's going to explain his project.
Okay. Hello, everybody. Is this on?
So, you got a little slide switch. I gotta wait 8 seconds.
I didn't realize that this was Hello?
Yep.
Okay. Hello, everyone. Thank you for coming today. My name is Sam Roberts, and this is my presentation on
what I'm making here, which is what I'm calling the virtual wave. I'm going to preface this a little bit and say that due to some unforeseen circumstances, I had slightly less time, so I had to change gears in a minute. So I don't have quite a year's worth of work like everyone else, but okay. So my objective for this is to work for the electrical labs and to create a product that's going to be a good demonstration piece for incoming students and prospective students that are coming to this school. So it needs to be simple to operate. We can't have a million buttons here for everybody to work with when they come in. It's got to be something you can just pick up and use. So it needs to also give the students some idea of what they can accomplish. So they want to come here and they want to say, hey, you know, I've been here for this amount of time. What can I do? So this project, I'm going to use some addressable LEDs, and I'll talk about that a little bit more here in a minute. So I'm going to show a quick video here. Get out of this. Okay, I'm going to show two videos here. So this first one is a video that we kind of had used for some inspiration. It's a cool effect, and it shows some movement of some LEDs with virtually no user input other than shifting the box. So, you know, I looked at this and I said, well, you know, I can take that idea and kind of try to make something else from that. So it's an easy to use item, it's handheld, and I'm going to take that and make it look kind of like what it would look like if you were rolling a water bottle around. So just to get an idea, here's just a video, quick video of the water bottle. You can see the water sloshing back and forth. So my hope is to create that sort of effect in my design and get those LEDs to create an effect that looks similar to that. Okay, the solution. So after I looked at those and had some brainstorming sessions here, so this is kind of what I've come up with. I want to create a cylindrical shape, and it's going to be filled with LEDs, so they're going to be embedded into it. And it's going to use a microcontroller, which we can code, and we can make the LEDs look how we want. And it's going to use an accelerometer. The accelerometer is going to be to detect the motion that's happening in this cylinder when it's rolled. And in order to create this effect, we're going to have to do some C programming, which is going to be involving that microcontroller that I just talked about. So I talked about addressable LEDs before. This is an example here. So you can see up in the corner there, everybody's probably seen something that looks like this. They're RGB, so they're multiple colors. And what I'm going to use here are a specific kind called WS2812s. Those are the most common strips that most people are used to seeing, and they use them in a lot of different lighting applications. Now these LEDs here, they're modular at both the IC, the chip level, and they're also modular at the strip level. So you can take these strips and you can just continue to chain them. So they have these connectors on each side, and they're long strips, so you can connect one of these output connectors to the next strip via the input connector here, or you can use this input connector to connect to your microcontroller, which is what I'm doing in this case. And I have multiple strips that are all going to be connected. So you can chain them together, and you can send your information in, and you can get all these different colors. Now it's important to talk about here what RGB means, and that's red, green, and blue. So that means that in each of these LEDs, there's 3 little modules, and they're each going to create one of these colors. So when you're coding this, you need to make sure that in order to create your color scheme, you can use a combination of these colors. Now, if they're all fully on, that's going to give you an effect that looks like white. If you just had red on, you're going to see red, or or green or blue like that. But you can combine the colors to create any color that you want. And there's 2 to the 24th power of combinations that this is going to create. So this is a variation of hues of the LEDs, colors, and also brightness intensities. So these can be adjusted a lot. You can code them, and you can really create some very cool visual effects. So I'm going to take these LEDs, and we're going to give them a specific layout. Now this layout here is going to look something like this. I'm just showing a 2D view here. You can kind of see the 3D view right here. This is the tube, and these are just some rough dimensions for it. So once I take those LEDs that I was talking about before, they're going to be in separate strips. So we're going to have these strips running across, which are going to wrap around the tube, and then on the end view is going to be LEDs that are going in circular patterns on the end to show like what the end of the bottle will look like. And it's going to be a total of 200 LEDs. It's 20 LEDs for each row, and there's going to be 10 rows. And then on the end is the circle, which is 95 LEDs. And these LEDs run on 5 volts, so you can use pretty much any power supply, but the important part is that you have enough current. If each one of these LEDs was on at the same time, they could pull up to 60 milliamps per LED, and that would be on full white. So that would be the full brightness for red, green, and blue all on at the same time. So this is an important consideration when you're thinking about an application like what I have, which is a standalone device. So you need to make sure that you size the battery correctly for this device. Now in this case, if we had half of these LEDs on, that would give us about 6,000 milliamps. So that would mean that if we used something like a portable power supply battery that was 10,000 milliamps, we should be able to run this for around a half an hour with no problems. And that's fine. When people are coming into the lab, they're not coming in for too long. So we're going to have plenty of time, and we're going to be able to take a look at it for as long as we want to. So now that I talked about that a little bit, you can kind of have an idea in your head of what it's going to look like on the outside. And so here's how I'm designing the strips. So I soldered all of these strips individually, and they are connected in series. So that means the input connector of one is connected to the output connector of the other one, and then they're all chained together. So in actuality, this is like one long strip, but they're just arranged in these circular patterns so that it gives you this visual effect here. Now, when I'm coding this, it's important to know which LEDs are which. So when you're looking at these LEDs, you're probably saying, who knows, what they're going to be. But it's really not too bad. So we're going to start. This is going to be the input right here at 0. And there's 10 of these circles in there. So each one is going from 0 to 19. And then we have all of these rows here. So we have 10 different rows of that. And so when these LEDs are past the data user, it's this tube, this clear tube, and inside of that is going to be embedded LEDs. So it's going to be all the strips that I was just talking about. And you can see the effect that it's going to be if it was half full. That's all these blue ones here. And so the nice thing about this strip is that we can put these strips on the outside and have a lot of space for all of our guts and all of our important pieces on the inside. So on the inside of this tube, we're going to have the STM32, which is a microcontroller, which is what I'm going to program to send the data to these LEDs. So the important part of that is that it can receive data from the accelerometer, which is right here. So the accelerometer is mounted in this tube in a fixed position, so when the tube spins, this accelerometer is also going to spin, and that's going to give us data. And I'll go into that a little bit more in the middle, but the microcontroller is going to take that data, and it's going to say, okay, now that I know this data, what am I going to do with these LEDs? So it's going to take the data, and then it's going to make a decision based on that, and that decision is going to be what I'm going to code for and to determine where it's going to move. So here is the physical build. This is what it's actually looking like, and you can see it kind of looks like a bottle. We've got the end cap here, which is the array that's the circular array, and then on the sides we have all of our strips, which are lined up. So let's get a little bit more into it here, the accelerometer. This is a pretty simple accelerometer. This is the number here, the ADXL335, and it's a simple 3-volt operation, and it outputs analog voltages. So you can see here, this is what you'd look at on the top, and then on the bottom you can see the pin out here. We have the X, the Y, the Z. Power is on the top, which is VCC, and then ground is on the bottom. So when we feed this accelerometer power, it takes that power, passes it through the module here, which is in the middle, and it sends an analog signal, which is a voltage, from one of these, depending on how it changes. So we're going to be most focused on the Z value for this. So if you look at this, and you say that the accelerometer is top side up, which is this side here that you're looking at. When you flip that over, it looks like this here. So when the top side is up, that's going to simulate 1 G of force on the accelerometer. And when you flip it over, it's flipping to -1. So we can use any of these three. We have X, Y, and Z, so it's a tri-axis accelerometer. I'm going to focus on Z for this project. Okay, so now we have our accelerometer values, and like I was talking about before, we have -1 and 1 for regardless of which direction we have this. If it's facing up, we're going to be seeing 1 G of force on it. If it's facing the other direction, we're going to be seeing -1 Gs. So what we need to do is we need to take the data that's in between here, and we need to map that to our LEDs that are on the tube. So we have 20 LEDs in the strip, so we need to map the distance between those LEDs, so 0 to 19 LEDs, and then the accelerometer value in the middle. So we need to take those values and we need to graph them so that we know which LED is where in relation to the tube and the accelerometer. So when the accelerometer sends the data, we want to know we need to send the data to, and then send that data on in. So in the programming here, we're going to be talking about a few different, a little more complicated things, but this is kind of how it's going to look. It's set up in these large arrays, so it looks kind of complicated, but really what it is when you see this half on here, so this would be like the half full condition for the tube. That is a 1 in a blue for all of these here. So when we want these LEDs on, those are the ones that are going to light up. And then what we need to do is we need to shift those in the array. So the array itself is not really going to change, but we need to shift these positions down or up depending on which orientation our tube is in. So if the tube rolls, we need to also move the LEDs with it. So we need to shift them up or down. And that's what being held in a function that I'm calling temp frame. So in my code, when you have the LEDs and you're coding for where they are, you've determined where they are, you know where you want them to be, you place that in this temp frame array, and then the send frame array, which I'll show in a minute in the actual code, is what's going to pass that down into here. So we can shift the LEDs around and the values in this temp frame array before we send them. So that's going to allow us to not always be sending them until we need to send them. So we can do multiple functions in this array and figure out where we need to be before we use up all the power to actually send those to the strips. So this is going to protect from some flickering. You'll see in mine that I still have some flickering, but that's a slightly different problem. But so yeah, this is how we're going to move the values into the strips. So for these LEDs, it's important to know what the protocol is to actually turn them on and turn them off. I had talked about before that they were RGB, and so that means they're red, green, and blue. So there's 8 bits for each of these colors. So if you had a full bright white on, you'd be sending all 24 bits of information. So we need to send a string of bits into this in order to turn these LEDs on. So how it works is we send one large string, and each LED takes their piece from that and then sends it down to the next one. So it's like if you had like a train and it's moving past a whole bunch of people and each person has to take a box. As it moves, it passes everybody a box, and then at the end, there's no boxes left. So each LED is doing that same sort of thing. So it's passing the data. Each LED is grabbing what they need from that, and they're passing the next unused data down to the next LED. And they're doing all that in a super quick succession, and so that's what's going to turn our LEDs on. And this is just a little chart here to show how we're turning the actual LEDs on. So in order to get that 1, which would be an on code, we need to send a longer high pulse. If we want them to be off, we're sending this shorter high pulse. And then the reset code here, that's what's going to tell our LEDs, okay, you stop listening for data and output the data that you have. So when we send that whole string of data, we need to tell the LEDs, okay, stop looking for data and use the data that you have now. So that's what this reset code is going to do. So in my code, we're going to have a little state machine, which means we're going to switch between different states based on the data that's coming. So the accelerometer is going to get us some data. We're going to start here, user input, which will be a button. And the user input is going to send us immediately into this idle condition, which is when it's sitting there, it's not moving. And if you roll the tube slowly, it's going to send it into this tilt condition, which is going to be for our slow roll, and that's going to keep the water pretty flat, pretty calm. But if you stop rolling it and it's sitting there, it's going to send you back into the idle state because it's now idle and it's not moving. And when if you're in the idle state here and you move it really fast, it's going to send you into the slosh state, just like we saw in the video of the water bottle, where the water is sloshing back and forth. We want that to look like that effect on our LEDs. So if you stop sloshing it and stop moving it fast, you're going to move back into the idle state and it's going to sit there. Okay, so let's get into a little bit of the code here. We're looking at send frame, which I talked about a little bit earlier. This is the piece that's actually taking our temp frame array and sending that to the LEDs. So what the temp frame is doing is it's taking the data that we had created, and then the send frame is going to take that data and it's going to send it to the LEDs. So what we're looking for the length and the width of the array, which is very important. Our width for all these is going to be 3 because we have red, green, and blue, which is for our RGB. And then our length is what we're going to change based on how many LEDs we have in here. So it's looking for the shifting. So you can see here I have this comment. This section here is what's shifting the bits. So we need to move those bits around to get our different colors and to get our different effects. So what we're going to do is we're going to send those through one of the data pins on the STM32 microcontroller. And the pin we're going to use for the tube control is pin B4. So this here is our address. We need to send we need to set up our address, and we need to send that data that we had through that line. And this is only a single line data transmission, so we only need to set up one pin for this to work. So then we're going to send it, we're going to clear that so that we can make sure that we don't have a bunch of stuff that we don't want, which is what's going to clear at the end after we've already sent this. And then we're shifting that, and we can change the delay and the rate that we're shifting it. And then we're going to just have a slight delay in there just so that we don't overcrowd everything. And as you can see here, the temp frame, which is what's going to be holding our arrays until we're ready to send them to the actual microcontroller and send them over the LED data, is just a normal char. It's an array. It's blank. It's just holding those in there until we've decided we want to pass it. So, like I was talking about earlier, we need to take our accelerometer data and we need to turn that into something useful. So, the first step that we had to do was we had to tune it. So, the accelerometer sends some very obscure voltage analog values, and we are taking those and we're going to pass those through an ADC, which is an analog digital converter. And lucky for us, there's one of those built into our microcontroller. So we're going to use that ADC. I don't have that shown up here, but once we take it from that, we're going to take that data and we're going to have a usable digital number that we can use in our calculations. So once we did that, we are going to take the Z-now value, which is going to be what the value is at any point in time of the Z-axis of the accelerometer. And you can see down in here, Z previous is equal to Z now. So we're using that, and we're going to take that, and we're going to figure out, okay, we want a velocity, which is the most useful thing for us. Acceleration isn't going to do as much for us. So we're going to take that Z speed and apply a sensitivity factor. So we can change that sensitivity factor, and we can change the dampening factor down here. So we can change how long we're going to see these effects for. And I'll show that again in a little bit when I show the actual code for that section. And in order to do this, we need a time, so we're setting up timer 2. There's multiple timers in this microcontroller, and we are going to use timer 2 for this one, so we can take the time and we can find a change in time, the delta time here, and then we are going to use that time to find our velocity. So now that we have that, we're going to look at a little bit of the code here. So this is a little bit of what I've got for the idle state. Now I have this idle state sitting in one position currently, and so what we're doing is we're finding the bottom. So we found the bottom before with the LEDs and with the accelerometer, excuse me. So once we know the bottom, we can take that and we can apply this range value, and that's going to put 5 sections of LEDs on either side of our bottom LED. So once we know which LED is the bottom on the ground, we can apply 5 around it to wrap around and fill up the half full look. And we also have a state here. So this is going to be our state idle, and this is going to be for when it's just sitting there. So we're going to use this, and we're going to copy that array that we just created here. We're going to copy this. If not, we're going to have the LEDs just show up black. So that's going to show that the rest of the top half of the LEDs are not going to be on. And the bottom half is going to be in this single teal color, which is the color that I created further in my code. It's just a combination of blue and a little bit of green. So now we want to have this sort of slower moving section here, and this is going to be what I'm calling tilt. So if you just tilt this, this is what we want. And so here what we're doing is we are taking that tuned value, and this is where we're doing our mapping. So we found the bottom. We know the bottom. We need to place the 5 rows on either side, like I was just talking about. And then we need to apply some sort of movement. So when this shifts and the tube rolls, we don't want it to stay in the same place, because then it won't look like it's moving. So we want to take that and we want to change this here. So we're applying our different columns and our different rows so that we can fill up all the LEDs we want. Again, we have the range, and then the wrapped portion of this is going to be so that if you turn it in the opposite direction, it will also shift the LEDs in the way that we want it, instead of only shifting them one direction. So this is going to make it multi-directional. And then we're going to use that at the bottom here. I had a little delay, but I got rid of it. It made it a little bit too slow. So let's look at the slosh code here. And it's a little bit of a confusing looking thing here, but it's not, it's not crazy complicated. So basically, again, what we're doing is that we are going to take all this stuff, and we're going to do a very similar thing. We're going to use the bottom again to figure out where we are. We're going to take that and we're going to shift it, and we're going to figure out how we want this to look. So what I have in here is I have a few different portions. So we need to make sure that we shift these for certain velocities. So when we have more velocity, we want to give it a little bit more of that effect, and we're going to try to create sort of a wave looking effect here. So we're going to shift the colors, and we're going to copy those into the temp frame like we did before. And this is showing the start and the end. So that's going to tell us where our LEDs are located and where we want them to be. So then we're going to say here, we don't want it, again, to just be on one side. So it's a similar sort of operation to the tilt, but it's just going to give us a slightly different effect. So then, we've talked a lot about the tube. We need to talk a little bit about the end cap here. So it's important. We need to set how many LEDs we have on the end cap, and then we need to use the velocity of this to change the position of these LEDs and make them spin around. And you'll see that on mine, it doesn't really work that well because the variation in the lengths of the strings on these LEDs is very hard to accommodate. I'm getting closer, but it still looks funny. So we only want to send data to the end cap. So we're going to enable a different port. Last time we had used port B4. This time we're going to use port B10. So in this section we're going to use B10, and we can hook our single wire data transmission line up to that port so we can only send it to the end cap. We don't want to send it all through the tube first and then into the end cap. It's more efficient if we can send it into each separate portion. So here's what we have. We have some different things going on in here. We've got a velocity scale, and this is going to adjust, like right here how I've commented. It's going to adjust how much movement you get per velocity. So if we get more velocity in there, we want more movement. So that's going to change that. And in the middle of the circle here, the number of end cap LEDs is going to be changing. So we want to make sure that we are moving these perfectly. I'm going to take that slosh position, and we're going to use that, and we're going to use the we're going to use the tube velocity and the velocity scale that we have up here to then determine how far we want these LEDs to move. So up higher in here I have an array of all of the multiple lengths for the end cap, and so we want to know how much we need to move those based on how much we're going to use the velocity and how much the velocity is moving. So we want to take those and we want to say here, this is our slosh width. So that's how many LEDs wide our biggest one is going to be. And we're going to take that and we are going to use that into the number of end caps. We know how many we have. We're going to take those and we're going to wrap them around so that we can continuously make motion around the circle. And then we're going to copy those again into the temp frame, send them as a single teal color, and those will create some movement in there. So the user interface, I'm currently just using this, which is the Nucleo dev board that we're using, because I want to keep it outside of my setup for now, just for demo purposes. Once it's finished, it's going to be inside with the battery. So I'm just using the buttons on here, and in the future, I'm going to add just a single push button just for starting that state machine that I had showed before. And so that'll be easy to use, not much user interface for that. So I think it's important to talk about, if I had a lot of time, if I had an extremely strong microcomputer here, how would I think about starting this to go through it? I think it's important to acknowledge how I would actually do it if I had tons of fluid knowledge and tons of time. So if you were going to do a full-fledged fluid simulation, you'd have to create some sort of grid-level particle format. So you'd need to move these around in a grid, and you'd have to calculate for the effects they have on not only the outside of the tube, but on each other. And so you could use some of these equations here, like the Navier-Stokes equations, which are going to give you continuity, momentum, and you're going to use different pressure gradient here. You're going to use the force on the body, which is going to be this, and then you're going to use diffusion, which is going to give you the effect of the movement. And you have to think about all the conservation of mass, conservation of energy, and conservation of momentum. And I did talk through this a little bit with a professor here, Professor Riley, and we determined that it wasn't going to work out really for my setup, but I think it's interesting information to note anyway, so that you know how this could actually be done in the real world if you had something like a fluid mechanics degree. So, anybody have any questions for me?
So on your sloshing, can you kind of say what the user would see?
Yeah.
Yeah, I have a little bit of a change in color on the edge, and it's kind of making like a wave over the other LEDs that are going to be on there.
Can you go back to the slide that showed the array on the center frame?
Sure. This one here.
That one. So this is the static case, right? The idle case.
Yes, this is the idle case. So
So can you, what would happen with like, what's the next case?
the tilting is just going to move all of these slowly up to the next one as the whole tube turns. So as it turns, it's going to just kind of follow the bottom.
And sloshing would be, you said a minute ago, changing the color.
Yeah, sloshing is going to just change the color, and it's going to change the position a lot faster than the tilt. So it's going to send them up, and then after a certain time, which was the dampening factor that I had in there, that's what's going to determine how long that stays up. So I can change the dampening factor for the increased velocity, so that when you move it fast, it goes up and down a little faster. If you move it slow, it changes in a little bit of a different rate. Yeah. Each. It's passing them on to the next one. So it has an address in the array here. So like if I wanted to just turn one of them on, I could name just this certain one, and I could send just that one, the data. But basically what it would be doing is all the other ones are looking at that, and they're saying, okay, that's not for me. And then when it gets to that one, it says, okay, this one's for me, and it will accept that data. Yeah, there's going to be, there can be some pretty big arrays if you connect a whole bunch of these strips together. It's 24 bits for each LED, and there's 200 LEDs, so it's whatever that is, 4,800, 48,000, 4,800. Yeah, it's 40. Yeah.
And just real quick, how much time does it take to send all?
It's very quick. It's milliseconds of time to send all of that. So, yeah. I'm sending it only when it's necessary. So it's only sending it when it needs to be sending the data for the movement. Yeah. How quickly could it? I don't know if I have a specific number for you, but it's very fast. It's not slow, that's for sure. Yeah. Oh yeah.
So it's a little bit like a TV set. You're flashing these images
Yeah.
continually based on your calculations, which are based on the accelerometer, telling you what's happening. And it's all faster than a typical image.
Yeah, it's very fast. Yeah, a typical person would not be able to come anywhere.
Frequency of the data transmission. I mean, you're sending down a single line,
Yeah.
0 and 101. So what is the frequency of that transmission? How many hertz, kilohertz, or megahertz?
I think it's 44 megahertz. No,
That's a different question.
I'm sorry.
4,800 microseconds. Like
Yeah, it's like 4. Yeah, so
200.
yeah, it's like 200 hertz for that transmission for all of them.
It's really fast.
It's very fast. Yeah.
And you know, as the length of the string of LEDs increases, that would be a problem, but you're not going to ever get that.
No, I won't have enough to make a big difference in that time.
Have you got a demo for us?
I do. It's not perfect.
Let's follow him over there. Take the mic with you.
I'll take the mic.
Yeah.
See that when it's just sitting here, we have it it's about in the middle here, and then if you move it kind of fast, you'll see that it's going to move back and forth, and you can see that the LEDs are going to change, like on this side. When you're moving it quickly like that, you can see that they're changing, and there's more of a waveform effect. It's a little easier to see it on this side. If you move it kind of fast, you can see, oops, something just became unplugged. They're now lighter. So when you move it kind of fast, you can see that it pulls up and then it falls back down. And that's the slosh that you're seeing there. When you move it, it's not going to really show the tilt super well because it's going to be a little bit too sensitive right now because I turned up the sensitivity for the slosh so that it's easier to see without spinning it around and pulling all my wires off here on the demo, but you can see that it has kind of a wave-like quality to it on there. So when it pulls up, you can see that it changes. You can see that it changes color on the end. The end is like up here, so it's kind of hard to see it, but that's the sloshing effect. So what I can change is I can change basically the lag factors of those, and I can change how much of the wave you're going to see. Right now you can see some of it, but not as much. There is an effect that you can have where it's a little bit of a randomizer, and so that's one of my next steps is to put that randomizer on the end of each of these LEDs here so that when you do the sloshing, that's going to kind of move each of them at a different rate. So I think with that addition, it'll look a lot better. Right now it has kind of a wave look, but it's kind of hard to tell. I can see it really well because I've been looking at these for months, but everybody else might not be able to see it as well as me.
So I already know the answer is the typical user is not going to pick this up and shake the bottle, right?
No.
You're just setting up for slow rolls.
Yeah, I'm setting it up for rolls right now. I would like to set it up for a tilt too.
You mean end to end?
Yeah, end to end. So like if you slide it this way,
It would all go to one end.
it would all go to one end or the other end here. And I can
roll it
definitely
slow
do that.
if you have that functionality working right now.
I have the sensitivity for the sloshing turned up a lot, so it's kind of like you're not really going to see it, but it's.
The idea if you crept it along,
if you creep
should
it
just
along,
shift
yeah.
the array, right?
I have that in there. It's just not really. It
It's not, I turned up the sloshing one so that everybody could see it without me just breaking off all of my wires. So it's there, it's hard to see. But yeah.
But if you turn the sensitivity down and you weren't having to worry about the wires, you would be able to just very slowly roll it along.
Yeah.
You essentially see the array of lit LEDs
Yeah,
shifting.
you can see it, you'll be able to see them shifting basically just slowly up to the next one. It's not 100% perfect because it's not perfectly linear between the axes with just the Z value that I'm using. So when you go between -1 and 1G, it's not perfectly linear, it's a little bit of a curve. So it's not like exact, but you can see the shifting. When it moves, it keeps it. You can tell that it's keeping it towards the bottom. It's not like flipping the whole thing over.
Are you intending to do some sort of curve fit or something to correct for that non-linearity?
Yeah,
so
definitely.
turn it into more of a linear result?
Yeah, I actually just recently figured out that that was what was causing my problem with that. So that's my next step is going to be to fix that and then add some randomization into the sloshing effect and just tune the timing of these ones on the end here, because I think that'll give a good way to see the sloshing on the end. The end cap is definitely going to be the easiest way to tell that it's actually sloshing when it does. So that's my next step, and I'm going to be working on that for the next couple weeks. So.
How are the end, on the ones on the side, they're linear around, how are they wired on the end cap? Is it a spiral?
Not quite. It's basically like they're all strips. So like it starts up here, and so this is one strip, and then at the last one here, it shifts to the next one.
Okay, so it's a
so they're all in series, but it's like
in a spiral.
it's just set up. Yeah.
Spiraling into the middle.
Yeah. It's all coming down into that singular LED.
Okay.
All right. Thank you, everybody.
Thank you. Yeah, let's give them a round.
Building suspense.
Yeah.
Uh-oh.
We'll have another little break in a few minutes after this presentation. So I'm going to turn it over to Caleb. He's going to talk about electric fireplaces.
My name is Caleb Kuzno, and my project was to design an electric fireplace. So the background on the project is that currently the electric fireplaces for the client that I was designing this for are all designed overseas. They kind of put together like a general aesthetic for the fireplace, and then they send that design off to some contracted company overseas. They make it and send it back. Because a contracted company has other clients, there's a lot of features that they don't get in their fireplaces. So the problem was to design or come up with a design that could be manufactured locally, has more customization options for the user, and ideally was modular so that different size fireplaces could be built using this sort of structure that I had created. The solution to that is to use individually controllable or addressable LEDs, create the flame effect using a rotating mirror that reflects lights, which is just reflective mylar, which is like a plastic strip, attached to a rotating rod, and then a metal panel with flame shapes cut out of it. And that flame cutout panel, as I'm calling it here, is actually adjustable, so the angle changes to adjust the height of the flames. And then all that should be controlled with just a few buttons so that it's not overwhelming or overwhelmingly large, at least. So this is kind of the general system diagram. So this is what the user would see from the front side. But then from the back, we have the LED strip down here. The LEDs emit the light, and the rotating mirror here will reflect that as the DC motor turns and kind of makes the flame look like it's rising. And it projects it through that flame cutout panel and into the one-way glass that's in the back. From the side view, again, we have the light coming out here from the LED, and then we can kind of see the yellow arrows are light beams coming through the flame cutout panel, which is the black dashed line right here. And you can almost see here how angling this backward and forward would actually change the angle that this light would be allowed through, and that's how we're changing the height of the flame. This is the existing system, so I was able to borrow some ideas from what they had been using, so I kind of reverse engineered this in a way. A couple things to note are that the motor they're using over here is an AC motor that does not have any kind of speed adjustment. This panel is completely fixed, and they don't have individually controllable LEDs, so all of the LEDs are one color or another, but they're all the same. This is sort of the interior of what my finalized system came out to be. So you can see here is the rod that angles this panel backward and forward. We have the LEDs that are kind of hidden by this rotating rod that's attached to a geared DC motor, which just rotates and creates that flame projection coming through here. So now I'm going to start talking a little bit about the actual LED control. So to control the LEDs, I use WS2811 control chips. So basically all it is just a small IC that takes in serial data. It turns that serial data into a PWM output, which is for a red, a green, and a blue LED. Very similar to what Sam talked about in the last presentation. The really awesome thing about these is that, again, similarly, it takes that one data inline and it buffers any data that it's not using and passes it to the next controller. It just improves the modularity of the system and kind of gives us the freedom to do everything we want to do with the LEDs. And then for the modularity again, so I'm working with 6-inch LED sections basically. So I needed to have high power LEDs, otherwise the LEDs wouldn't be visible in a lit room. So you can kind of see here, this is just sort of a poor rendition of the control circuitry that's used to actually control the high power LEDs, and these are about 6-inch sections, each with 5 LEDs on them, and the idea is that they chain together for as many PCBs as you need for however big a fireplace you're trying to create. For the actual lighting system circuitry, we kind of see these black boxes here, as we'll call them. Each of these is representative of a single LED's worth of circuitry. So that's a single RGB LED's worth of circuitry. So over here, this is the actual inside of that black box. We've got 2 transistors and a few resistors for each LED, and then we're just powering this guy up with those, the outputs of these power transistors. We'll get into that a little bit more in the next slide. Again, modularity is the big concern here. So all of this is done with the idea of chaining these PCBs together in mind. The big struggle here for this entire project really was the current amplification circuit. So the controller I was using was capable of supplying roughly 18.5 milliamps of current to the LEDs. To reach 1 watt, depending on the color, you need at least 300 milliamps. So I needed a transistor that would allow me to pass through 300 milliamps. The problem that I ran into is that when you have a lot of power coming through a transistor, you also have a lot of temperature. And with temperature, the current amplification characteristics of the transistors change. So in order to stabilize that, we actually decided to use 2 of these same transistor. And the way that it works is that at the current that we specified, which is 300 milliamps, this resistor is going to drop, it's roughly 0.56 volts, which is going to activate this transistor and just feed any current back off into this base. This is just a pull-up resistor, and all this resistor here is for, R3, is just to ensure that when the WS2811 enables the circuit, this is actually pulling all the way low. It has to pull low because this chip is a grounding chip. So every time that we're trying to enable or turn on the LEDs, this chip grounds the circuit, which is also why we need this pull-up resistor. So we are creating this sort of effect by using PNP transistors and then just pull-up resistor, and again, just another resistor on the base to make sure we pull it all the way down. For the actual LED control, this is kind of an abstract of the actual code that runs the effects. So for the fire effect, I've got 36, we can see here this is a 36 by 3 array of data. And the 36 is the number of lines or LEDs, and those 3 columns represent red, green, and blue. Each of these colors is a separate shade of orange, and then it repeats itself. So the idea here is that using that send frame function that Sam covered, I'm actually taking this and starting at a different point in this fire step array that I've created. And in doing that, I've created a bit of, it shifts the shades of orange kind of down the line. It looks like the LEDs light up as 6 different shades of orange, and each time that this cycles through, those LEDs shift 1 spot over to the right. Yeah, that's pretty much it. So this is a waveform. This is about 50 microseconds from start to finish. So each of these each of these cycles for each bit for each LED is about 1.2 microseconds. We have 48 pulses here, so it's a little bit over 50 microseconds total. But the idea is that this first section, these 8 bits are green, and then we have red, and then we have blue. And then this is the split between the 2 LEDs, and we have the same thing repeating. The on-time versus off-time is a little bit different. It's actually created some complications in the actual demo of my project. But what we have here is we have all on bits for red and all off bits for blue to kind of demonstrate how we're still sending ones. It's just about the difference in the on time for those ones that makes the controller register whether the LED should be on or off. And then back to the rotating mirror. I briefly mentioned it before, and now we're just going to go into the control circuitry for it a little bit. We have a geared DC motor, and this is just a flyback diode. It's all controlled by a single NFET. The decision to do this was basically just so that we had more speed control, or any speed control really, because the existing units that they were using don't have any speed control. So the idea was that using simple PWM control, we can change the speed of this motor, and therefore change the speed of the flame, which just creates the effect of looking more or less intense. This is, it's fairly self-explanatory here, but for the slower side, we have 25% duty cycle, which is just the on-off time, and then we have a 75% on the higher end. These, because I didn't need to have precise speeds, there was no control system required, so just controlling these duty cycles for the PWM output was enough. For the actual DC motor control, I made use of the STM32's hardware abstraction layer, or HAL system, which is basically just a graphical user interface that lets us configure and then toggle or sort of perform all sorts of functions with various different parts of the microcontroller. So I used the HAL system to configure the motor, and then I actually just forced the value that I wanted inside of the register for the duty cycle. So this is a 75% duty cycle just forced into the proper register. So for the flame height and backplate control, all I did was I put a servo motor behind the panel, and I put hinges on this cutout panel. And it's connected with a linkage. So, again, using PWM, we're just controlling the angular position of the servo motor, and then therefore the angular position of the the flame cutout panel. It's a really simple circuit. It's kind of important to note that it's not really the same type of PWM control as what we used with the DC motors, because the DC motors are going to spin basically freely or continuously, whereas really this servo motor is only going to have about 180 degrees of movement. So depending on the PWM input, we're actually setting the position of this lever on the servo motor. And in the case of my project, we're getting about a 3-inch range here, which translates to about a 3-inch difference in the low height flames and the high height flames as well. For the code, we're just kind of doing something fairly simple. We use predefined variables that can be seen in this set PWM function right here. All that's doing is defining the period of the servo motor and then the actual on time for the servo motor. So it's, again, just very simple. We're using over here, this is actually this whole thing is one big state machine. So we're using a function called, or a case called maybe pressed to perform button debouncing, so that we don't get sort of undesired effects. And then we have our low, medium, and high states. And this is all running continuously while the fireplace is operating. So all of the functions are performed simultaneously using different state machines. And I'm going to get into that in the next slide, actually. So for the user control, we have these handle functions here. Handle speed, handle flame, and handle height. And they all look fairly similar. It's just one, each of them is a simultaneous state machine which is basically just performing an action that we're saying, okay, well, we want to check for this button to be pressed, and if the button's pressed, we need to change states. And that's how we're actually cycling through. So the state machine diagram is over here. It's a simplified diagram, but the gist is that we go from a standby mode using an on-off button, and then from any of these states we can shut back off. This button, PB4, push button 4, is used to put the entire system into standby mode or take the entire system out of standby mode. And then we use push button 3 to cycle through the heights. So it's just low, medium, and high, and we cycle through. Using state machines because they're very good at pattern recognition. And yeah, just we step through these, and I can't remember what I was going to say. So
Caleb, on that last slide.
Yeah.
What are push buttons to it?
Oh, yes. So, thank you. Push buttons 2 and 3 are what controls the speed and the flame. And that's what I was going to say. Thank you. So, the idea is that each of these, again, has its own separate debouncing, but all these functions are performed without any kind of blocking delays, which is just a delay function that would stop the code from running, so that we can keep stepping through these, and also so that what we're doing is it's performing these actions simultaneously, and to the user it appears like our program is actually handling different inputs simultaneously, even though the CPU we're using is actually only one core. For my timeline, the only really important date here is actually the PCB modules. Obviously, there's big milestones mixed in here, but the one that was really make or break for this project was having the PCB modules ordered. The circuit was different components, but specifically the high-power LEDs. It's not particularly cheap, but and also the cost of development is more than the cost that it would actually cost to produce one of these. But the rough production cost of this 18-inch electric fireplace was about $410. Questions?
Can you go back to that state machine slide?
Sure.
I think when we talked about this, a good analogy is the bells and the flashlight.
Yes. Yeah. So, a great analogy for what we're doing with this all of this functionality is like any kind of cheap flashlight, where if you press the button, it'll change brightnesses. So you cycle from off to on, but very bright, or medium brightness, low brightness. That's essentially the functionality that we're looking for with these state machines, is that we can perform, or we can toggle lots of different settings using very few inputs.
Same thing with the speed.
Yeah, we have 3 toggles, so they're, well, 4 if you count the power button.
Right, but how many different speeds?
So we have 3 speeds, 3 heights, and currently 3 different LED effects. All of that is really easily changed though, so that's part of kind of the modular design, is that anything that we wanted to fine-tune could be fine-tuned later on. The idea is really just to prove that we can build the electric fireplace locally.
Steal your mic just for a second. This has nothing to do with this presentation, but how many of you own an electric fireplace? That's what I thought. You have to understand that this is very much a California thing right now, but as global warming takes over and they start restricting your use of wood and whatnot, you may soon own one of these. So this is maybe in your future. Okay, I'm going to ask Caleb to go do the demo. Come on over. It's kind of fun to watch.
Kind of.
No problem.
supposed to be a breathing effect, but you can see that the way that the reflective strips reflect through, and then with the sort of diffusion that the glass is doing as well, because we have a diffusion film on the back, it mixes the colors really nicely, and it creates kind of a cool flame light look. So we've got low, medium, which is not much
It's like
lower.
look at these kind of slowly, Caleb.
Yep. And then the high flames, and then for the speeds, we started at high. Beginning to think that okay, there we go. So this is the medium. I think this is low, but I can't really quite tell. It's a little more obvious when we don't have the box on top. You can actually see the motor spinning. But
So you're just playing with your 4 buttons over
yeah,
there.
so all I'm doing is just hitting the buttons over here.
He's got 4 buttons over there. But he's plugged each one the end user. Yeah.
Right. So the idea is that we're just, and that's where those state machines come in again. So all we're doing is just hitting one button, and that's low. Same button, medium. Same button, high.
So it's the height of the flame.
Right, and that's the height of the flames. And then the standby shuts everything down. When we turn it off, it comes
So
back.
do the low and explain what's happening with the servo and tilting the flame.
Yeah, I think
up.
that'll actually be a little easier if we don't have this on.
If you come to the side, you can actually see what's going on.
Yeah, so when we're adjusting the height, all that's happening is this servo motor is turning, and it's angling this panel forward and backward. And again, all with just one button. And then the speed. There we go. Medium, low, and then the effects. So because I'm getting some data corruption here, it's a little bit harder to see that it's just shifting, but in the moments where you can tell, you can see that the LEDs are just kind of shifting toward me. And then just again to demonstrate that initial effect, because I think it's rather cool. So we just start in the middle and then expand outward.
Let me add a rating here. You're welcome to come up and get closer. Just don't stare at the LEDs. They're pretty bright.
They're really bright.
It'll stop burning eventually, though.
Caleb is an electrical engineer. As you can see, there's an awful lot of mechanical design here. We're not grading him on mechanical design, but he needed to put something together to test out all the electrical theory and whatnot. So, considering the fact that it really is electrical design is super responsible for the software design, state machines, those are the things that he's fundamentally doing now. That we'll find tuning to do, but he certainly has a workable product that sort of demonstrates the key ideas of modular design. And turns it off, come up closer and see the printed circuit board you design, and see how they work together. And just this product now is manufactured in the U.S. That's a good thing. Because before, all of that was a sealed box, and you had to buy the whole box for China. They were the sole supplier. So it opens the door for the client to do what they want with this design. I was going to mention earlier when I asked about the academy, these sort of things are appearing in hotel lobbies and all kinds of situations where the size of the fireplace can be as wide as you want it to be. It can be a whole width of the lobby. That's the kind of thinking that's going into this. You don't have your fireplace, and you can have heat removed. You would have to actually install like a heater in the suite. What may be tied into the heating system of the home is just for the room. So you don't have any fear of burning yourself. Just get the aesthetic. You can have the aesthetic anything you want to do. And you can have purple flames if that makes you feel happy. You don't have to be stuck with this. So,
I hadn't exactly ironed out which.
by all means, unfortunately, they want to leave in a few weeks. They all are getting great job offers, as you can imagine, because they have a skill set that most of us don't have. So that's what we're trying to do here, is turn these students into working engineers, and I think we were doing a pretty good job with that. So let's take a few minute break, grab some more refreshments, we'll get started again in 5 minutes.